Hi, this is Somaiah working as assistant professor in the Department of Mechanical Engineering. Welcome back to the fluid mechanics and hydraulic machines. So today I'm going to discuss about construction of Moody's diagram. Also, the importance of dimensional analysis. The purpose of Moody's diagram is to determine the one of the factors from these three factors. One is the Darcy's Weisbach friction factor. F we can determine from a Moody's diagram, and we can determine Reynolds number also. We can find another one, the roughness, the relative roughness of a material, pipe internal surface of a pipe. These three parameters we can determine if two parameters are provided, another parameter we can determine by using the Moody's diagram. Before the Moody's diagram, in order to find out any of these three parameters, the one equation was developed by Colebrook-White equation. The Colebrook-White equation is made into the diagram by the Moody's. So thereafter, it was named after Moody's diagram. The importance of Moody's diagram is to determine the friction factor F and Reynolds number. Otherwise, we can determine the relative roughness of a surface of the pipe. So the friction factor we can determine. We have the various for flow regimes, and we can have different the empirical relations. So suppose if the Reynolds number is less than 2000, so then that indicates a laminar flow. If it is less than 2000, that indicates a laminar flow. If it is a laminar flow, we can find out, we can use 64 by RA. Otherwise, if it is a turbulent flow, F is equal to 0.079 by RE power 1 by 4. So these different relations we can use to determine the friction factor if the Reynolds number is between 2000 to 4000. So this is applicable over here. This is up to 2000 only. So less than 2000, this is in between 2000 to 4000. But whenever the Reynolds number increases more than 4000, if it is greater than to 4000 and till up to 10 power 8, up to 10 power 6, etc., in that cases, we can use the Moody's diagram. So because the empirical relations are applicable up to Reynolds number is 2000 to 4000, and beyond 4000 it is not applicable. There is no empirical relation to determine the friction factor in order to find out the major loss of a fluid while flowing through a pipe. HF equals to 4 FLV square by 2 GD. So there we can't find out the loss of it due to friction. This is also called as major loss. Otherwise, the Darcy's friction factor. The expression, Darcy's expression for major energy loss. So this is not much useful behind that. So in order to find the major energy loss behind behind the Reynolds turbulence also, as the turbulence is going on increasing, so the loss of it due to friction we can't calculate behind for in such cases we have to adapt the Moody's diagram. So that is a limitation of these relations because once Moody's diagram is not there, we can't calculate the HF. Loss of it due to friction can't be calculated. So in order to find that, the Colebrook equation was developed. The Colebrook equation is converted into a diagram. So that is known as Moody's diagram. So the majorly the limitation of friction factor in order to calculate in the heavy turbulences also. Turbulence as it is increasing beyond 4000. So another one is Reynolds number. Based on Reynolds number only we can divide the flow regime. So based on Reynolds number, if it is less than 2000 and in between 2000 to 4000, if it is greater than to 4000, so like this. But what is Reynolds number? Reynolds number is the ratio of inertia force to viscous force, that is rho Vd by mu. So or Vd by nu. So in terms of kinematic viscosity, this is in terms of dynamic viscosity. So where rho is the density, V is the velocity of flow, and D is the diameter of a pipe. So and mu is the dynamic viscosity. So if you substitute all these parameters, we'll be getting one value. So that is maybe 3000 or 4000 or above 4000, some value will be attained. So based on this value, we can decide which type of flow regime it is. So that is a Reynolds number. That Reynolds number can be calculated, or it can be read. From a chart directly. So that is the importance of Moody's diagram. We can read it without calculations of Reynolds number. We can read it directly from a chart. So that is Moody's diagram. So provided the Darcy friction factor is required, and another one is relative roughness of the particular pipe is required. Here, relative roughness is required. Relative roughness and this friction factor and relative roughness. Once these two parameters are provided, so then we can calculate a Reynolds number. So based on Moody's diagram, any two parameters are required to determine another parameter. So therefore, here we can understand Moody's diagram is constructed based on these three axes. So one is horizontal axis on which one parameter can be read, and two y-axis. So therefore, we can determine any one parameter from the given two parameters. So that we will see on x-axis. So what is plotted, and on y-axis f is plotted, and the relative roughness is plotted on another y-axis. So the most common classification of flow regime is according to the Reynolds number. So that may be laminar flow or transition flow or turbulent flow. So, but the transition is nothing but a conversion of laminar into turbulent. The zone, the period in which the laminar flow will be converting into a turbulent. That particular zone is known as transition zone. So, an increasing Reynolds number indicates the increasing turbulence. So, as can be seen from Moody chart, also Darcy friction factor is highly dependent on the flow regime. For practical purposes, the Reynolds number is less than 2000. That indicates the laminar. As accepted transition Reynolds number of flow for circular 2300. The head loss is proportional to velocity rather than velocity squared. So thus the friction factor is inversely proportional to the velocity. The Darcy friction factor for laminar flow shows a consequence of Feisel's law, and it is given by following equation. For circular flow, 64 by RA, as we have discussed earlier, and for non-circular pipes, K by RA, where K lies in between 48 and 96. So for different cross sections, so there are different K values are given. So while solving the problems, we have to choose according to the requirement. Darcy friction factor for transitional flow. At Reynolds numbers between 2000 and 4000, the flow unstable, the result of the onset of turbulence. So these flows are sometimes referred to transitional flows. The Darcy friction factor contains large uncertainties in this flow regime and is not well understood. Darcy friction factor for turbulent flow. If the Reynolds number is greater than to 3500, but in practical, so that will be greater than to 4000. There will be taken as, but once the critical Reynolds number and based on the critical velocity, if it is taken, that is accepted up to above 3500. So in this flow regime, the resistance to flows follows the Darcy Weisbach equation. It is proportional to the square mean velocity. The Darcy friction factor depends strongly on the relative roughness of the pipe's inner surface. The relative roughness that we are going to determine the inner relative surface roughness of a pipe. So Darcy friction factor for turbulent flow. So in this, the most common method to determine the friction factor is a Moody chart. Once the Reynolds number is greater than to 4000, then we do not have the proper equation, proper relationship to determine the F. Therefore, the according to Colebrook equation, the friction factor can be calculated from this equation as 1 by root f equals to minus 2 into log 10 into epsilon by 3.7 dH plus 2.51 by Reynolds number root f. So this is a friction factor for which we have to use this equation according to Colebrook-White equation. So but this equation is converted, d is the diameter of a pipe. This is converted into a chart by this Moody's. The Moody's diagram is the converted the equation of Colebrook-White. So which is also known as Colebrook-White White equation, expresses the Darcy friction factor F as a function of pipe relative roughness E by dH and Reynolds number. So this is taken as x-axis. Reynolds number is taken as x-axis and relative roughness is on y-axis. Another parameter F is on another y-axis. These three parameters so given by Colebrook-White equation, and this Y equation is converted into a chart by Moody. So in 1939, Colebrook found an implicit correlation for the friction factor in round pipes by fitting the data of experimental studies of turbulent flow in smooth and rough pipes. So this is the Colebrook-White equation converted chart. So the otherwise Moody's diagram or Moody chart. So here there are three parameters. So if any two are provided, another one can be calculated, or another one can be read from this chart. So on y-axis there is a friction factor F. So there as y-axis is increasing, so this is taken from 0, 0.01, 0.015, 0.02 and so on up to 0.1. So this is drawn between 0 and 0.1. And the Reynolds number is drawn from 0 to 10 power 8. 0 to 10 power 8. So the Reynolds number is, according to Reynolds number, the laminar flow will exist up to 2000 of Reynolds number. So up to 2000 there will be laminar flow. Laminar will be existing up to 2000. So there therefore up to 2000 we can see the laminar flow will be existing, and afterwards there will be transition flow. So then afterwards there will be a turbulent flow. These three regimes are shown here so clearly. So in this region laminar flow will be there, transition flow and turbulent flow. So but if it is a laminar flow, the relationship is 64 by RE, and in turbulence once 4000 is increased, so we'll use up to 0.079 by Re power 1 by 4. So this will be used up to certain limit, up to 10 power 6. If it is up to 10 power 8 or more than to the 10 power 6, whenever the Reynolds number is increasing beyond 10 power 6, so the empirical relations are not applicable. So in that cases we have to use Moody's chart. So but the transition indicates a conversion of laminar into turbulent once relative roughness is known. Relative roughness is on another y-axis, on right hand side y-axis, on left hand side y-axis is friction factor. Relative roughness is also drawn from 10 power minus 6, 0 to this is 10 power minus 6, 5 into 10 power minus 6 to 0.05. So this is beginning of 10 power minus 5 or 10 power minus 4. So beginning is not 0, but it is beginning from negative 10 power minus 6 to 0.05. These are the relative roughness lines. The horizontal, the blue colored lines are relative roughness lines. So if relative roughness is 5 into 10 power minus 4 and the Reynolds number is 10 power 6, then they have an intersection over here. So that means based on this we can find out, as y-axis is increasing, the roughness is also increasing. As it is decreasing, the smoothness will increase. Smoothness of a pipe will be increasing, so that we can say which type of surface roughness is having by the particular pipe, whether it is smooth or rough. These types can be expressed by finding out the relative roughness zone. And so then we can find out, so for the intersection of Reynolds number, this is 10 power 6 and this is 5 into 10 power minus 4. So from this I can draw one horizontal line onto left hand side y-axis. So it intersects somewhere here in between 0.02 and 0.015, say 0.018. So 0.018 is a friction factor. So here I didn't use any relation of 64 by RE and otherwise 0.079 by RE power 1 by 4, etc. Without using any equation, I can get the value from a Moody chart. So if Moody chart, in this Moody chart, once friction factor is provided and Reynolds number is provided, you can draw and intersection, and from this you can extend on to the right hand side y-axis to get the roughness of the pipe. Internal surface roughness of a pipe can be obtained from this. So this is the importance of a Moody's diagram. So for hydraulically smooth pipe, the turbulent flow, Reynolds number less than 10 power 5, the friction factor can be approximated by Blassi's formula F equals to 100 into RE power minus 1 by 4. It must be noted at very large Reynolds numbers, the friction factor is independent of the Reynolds number. So this is because of the thickness of laminar sublayer. Viscous sublayer decreases with increasing the Reynolds number. For very large Reynolds numbers, the thickness of laminar sublayer is comparable to the surface roughness and it directly influences the flow. The laminar sublayer becomes so thin that the surface roughness protrudes into the flow. The frictional losses in this case are produced in the main flow primarily by the protruding roughness elements, and the contribution of the laminar sublayer is negligible. So in this diagram we can see if it is the internal surface roughness of a pipe is enlarged through a microscope, we can see how the roughness will be there. So for a rough wall, so these projections will be high. So that is given by epsilon. So here the epsilon is very small for a smooth pipe. So this is very small heights. We can find out very small roughness. So whenever it is enlarged, based on this only the relative roughness will be calculated, epsilon by d, by which we can calculate in the previous diagram in Moody chart. If you come back to the Moody chart, we can find E by d, epsilon by d is nothing but relative roughness. So the epsilon can be calculated by using the height of this roughness. So this is nothing but epsilon d. In order to find out epsilon by d relative roughness from a Moody's diagram, we have to find out the epsilon from these diagrams. For example, determine the friction factor if the diameter of the pipe is provided and the Reynolds number is 50 into 10 power 6 and the epsilon is given. So in the previous diagram the epsilon is 0.035. If it is 0.035 that is provided, then we need not to come across of this and we need not to read from the diagram. If it is not there, if the diagram is provided, from the diagram we have to consider that value and we have to substitute into the problem so that we'll get the various we can see various parameters can be revealed here. From this diagram we can see the 50 into 10 power 6 is given and this is 5 into 10 power minus 5 as epsilon by d. Epsilon is 0.035. See from this diagram from the previous slide we can see 0.03 by 700. So we can get epsilon by d. Epsilon by d is nothing but 0.03 by 700. So 5 into 10 power minus 5. So that is marked against on y-axis at in Moody's chart, and Reynolds number is 50 into 10 power 6. If you mark these two parameters, say this is 50 into 10 power 6, 50 into 10 power 6, and this is 5 into 10 power minus 5, and I got your intersection over here. Okay, then if you extend this line onto left hand side y-axis, then it will be intersecting at a point 0, 1, 1. So as this is 0.01, this will become 0.011. So then 0.011 is the friction factor. So for this, we need not to use any relationship. Once a coincidence is found from a Moody's diagram, from that simply we have to extend onto the y-axis, then it reads the required friction factor. So this will be utilized for the calculation of, again, we can calculate loss of head due to friction in a Darcy's waste-bag equation, 4FLV square by 2GD or FLV square by 2GD. So from this diagram, we can calculate HF also. So in order to calculate F, we need Moody's diagram. If the turbulence is more than 2 10 power 6, etc., where the empirical relations won't work out. Dimensional analysis is a mathematical technique which makes use of the study of dimensions as an aid of the solution of several engineering problems. Each physical phenomenon can be expressed by an equation composed of variable or physical quantities, which may be dimensional and non-dimensional quantities. So for every physical entity can be expressed in terms of an equation. That equation can be analyzed by using dimensional analysis. This will be useful in the analysis of flow field problems. In a flow, we can divide that flow into various equations and we can analyze by using dimensional analysis. Dimensional analysis helps in determining a systematic arrangement of the variables in the physical relationship and combining dimensional variables to form non-dimensional parameters. In the study of the fluid mechanics, the dimensional analysis has been found to be useful in both analytical and experimental investigation. Some of the uses of dimensional analysis are testing of dimensional homogeneity of an equation of fluid motion, also deriving equations expressed in terms of non-dimensional parameters to show the relative significance of each parameter, so planning model tests and presenting experimental results in a systematic manner in terms of non-dimensional parameters, thus making it possible to analyze complex fluid flow phenomenon. Dimensions. The various physical quantities used by engineers and scientists to describe given phenomena can be described by various quantities. These quantities, known as fundamental or primary quantities, so they are M, L, T and T. The fundamental quantities are M, L, T. And the temperature is especially useful in compressible flow. All other quantities such as area, volume, velocity, acceleration, force, energy, etc. are termed as derived quantities. The primary quantities are MLT and T and theta. So the derived quantities will be utilizing the primary quantities and they will be derived. So for example, the dimension of force can be expressed as a force equals to mass into acceleration. So mass is m. Mass is from the fundamental quantity. Mass is m, and length is l. Time is t. So by utilizing the fundamental or physical quantities, and the derived quantities can be expressed. The derived quantity for acceleration, the unit is meter per second square. The meter can be expressed by L by T square, and F equals to M into L by T square, where M is mass. M into L by T square, it can be expressed as ml T minus power minus 2. So therefore, the rectangular bracket signifies that the dimensions of quantity are being considered. So the dimensions of mostly used physical quantities are L, M, T, and remaining all are they are derived quantities only. By utilizing the fundamental quantities, they can be derived. Dimensional homogeneity. Means the Fourier's principle of dimensional homogeneity states that an equation which expresses a physical phenomenon of fluid flow must be algebraically correct and dimensionally homogeneous. An equation is said to be dimensionally homogeneous if the dimensions of the terms on its left hand side are equals to dimensions of the terms on right hand side. LHS is equals to RHS. Then we can say the particular equation is dimensionally homogeneous. So if LHS is equals to RHS, then we can call. So by using this expression, we can see whether it is dimensionally homogeneous or non-homogeneous. So v equals to root 2gh. So where v is the velocity, its unit is meter per second, then I will get a L t power minus 1. So the on left hand side, on right hand side I have root 2gh, where g is L by t square and h is a head, that is meters. Meter indicated by L by t square into L square by t square. So then it can be Lt power minus 1. So as root and square is cancelled. So then right hand side is Lt power minus 1. I got on the same thing I got on left hand side also. So therefore LHS is equals to RHS. When particular equation is LHS, following the LHS equals to RHS, then we can call it as is a dimensionally homogeneous. Methods of dimensional analysis. There are two methods. One is the Rayleigh method, another one is Buckingham 5 method. Rayleigh method is dimensional was proposed by Lord Rayleigh in 1899 for determining the effect of temperature on the viscosity of a gas. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.